Almost rejected either. Okay, we are now recording. Let me go over a few fairly important items. Now, number one, I can't remember where the discussion went in this class. I know in some classes I got one set of feedback, another I got quite different, and I was fairly confused, and finally I asked one, well, okay, it's about student course evaluations. Have y'all seen them? Okay. Yeah, so this is what this class said. When I went to, I think, my afternoon class on last Thursday, asked them the same thing. He said, oh, yeah. It was some class later said, oh, yeah. I said, well, how do you know about it? Email, did it just come out? No, it's been here for, I thought. I was completely confused. And then I mentioned something to someone. They said, well, some people got the email and some didn't. I thought, that doesn't make sense. They sent it to all students. So then I don't know why I happened to think, well, what was the title of the email? What was the subject line? He said, oh, it's the one that we did the Student Government Association voting on. I went, oh, did it say anything about student course evaluation? I don't think so. So that's why. If y'all space by that one, that's the one. So go back to that. Have you deleted it, or is it still out there somewhere?
I still have it.
Okay, good. Go back and check, and I bet you'll find somewhere in there is a link to do student course evaluation. Yeah. Seems like to me the student course evaluation should be the subject line, and also you could vote for government association too, or maybe put them both in the subject line. But to completely hide it in there, not a good idea. So please check that. You'll have a link. You can go directly to it and get it done. All right. Now, that's one thing. Number two, this, my favorite class. How many research papers do I have from this, my favorite class? I don't. Zero. Zero research papers from this, my favorite class, okay? And Thursday's the deadline. I mean, no more weekends, okay? That means before class on Thursday, I need to have it in my grubby little hands, So turn them in today, tomorrow, or when you come to class on Thursday, okay? Easy. What's that? I said easy. Okay. And also, any tests you have outstanding, I need those in on Thursday as well, okay? Huh?
I said easy enough.
Okay.
I said easy enough.
Okay. All right. So please get everything turned in by Thursday, because guess what, Thursday? I'm going to be turning everything back to you. And I can't return research papers. Number one, I won't have them by then. But number two, I have to hang on to samples for student writing, so I can't return those ever. Or you can come back and get them in 3 years when they don't need them anymore. I may not be here in 3 years, but you can come look for them if you want to. Okay. If you care in 3 years. Okay. And then, but your other papers, I want to get all those off my stack. I would have had them back to you already, but there's some that I haven't gotten. The test one, I have at least one. Yeah, one that hasn't turned in test one. Test two, I've received one. And test three, zilch, zero. Oh, yeah, I may have gotten the first one in last week, possibly. I don't remember now. And I did get one in, and I worked on that some this weekend, and it was, I believe that was test three. Okay, so there's that. Any questions on that before we start? Or any questions? Oh, and by the way, on Thursday also, I will be giving you 2 tests, and they're both very short. One will be the Chapter 6 test, what we cover in Chapter 6, and the second will be the Comprehensive Final, which will be, again, very short, just a few questions from each chapter. And it's stuff you've already been tested over, so you'll find it, I think, pretty easy. Okay? So 2 much shorter tests than the other tests have been. Okay? Much shorter. Okay. And I think you'll find it easier as well. All right. Any questions before we get going? All right. Then we're dealing with applications. This is on page 411. Either of you also softball players?
In high school.
You there, okay. I don't know if you knew your dimensions then, but the pitcher's mound, let's see if we have a picture here. Here it is. The pitcher's mound on a women's softball field is 43 feet from home plate, okay? It's shown in this figure. The pitcher's mound is not halfway between home plate and second base. It's a little further back. How far is the pitcher's mound for first base then? Okay? Strange sort of question, but still there. Okay? So if you're trying to pick off a runner at first, how far does the pitcher need to throw it? Okay? They don't usually have to calculate this, but so how are we going to find that? Now, a couple of things. They show the dimensions here. 60 feet between each of the bases, first, second, third, and home. And this makes a perfect diamond, but also a perfect square. So these are, number one, equal length, which we know, but also equal angles. Okay? Now, the pitcher's mound is in line with second base. It's not halfway between, but it's in line with it. So we know this angle here has to be 45. Okay? And we know this, they just told us that the home plate to pitcher's mound is 43 feet. Okay? Now, has it dawned on you why they have the lettering as they do? They made this home, that makes sense, and that first base, which sort of makes sense, and that pitcher mound, which sort of makes sense. But you notice what they also did with the lengths. Since those are the places, they also, the capital letters represent the angles, okay, and the smaller letters represent the things. So that's why this is your F over here, even though this is the pitcher's mound, they give it F as if it has something to do with first base. Well, it does. It's the side opposite the angle that would be first base. And this is the side opposite P, the pitcher's mound, so they call that little P. And what we're looking for is little H up there, which has very little to do with home plate itself, but it's the side opposite the angle there. Okay. So, with this much information, can we solve the problem? Can we answer the question with just that information? If so, how would we answer it? Yes, law of sines does not work because you only know one angle and you don't know the opposite side. Okay? You do know the two sides and the included angle, which does. I'm sorry.
What's up, your office hours tomorrow? 10 or what's that? 10 or 1:15?
Friday,
Your
yes.
office hours tomorrow, 11 to 2.
Tomorrow, tomorrow's Wednesday. 11:15 until 1:15.
That's on the Birmingham campus?
No, here. I'm here.
Okay.
Now, I'm over there in the evening. I have a 4 to 6 o'clock class over there in the evening. But wait. Let me back off. 11:15 till 2 tomorrow. I'm sorry. 1:15 today. 11:15 to 2 tomorrow. And that's here on this campus. But then after the 3:15, my 2 o'clock class gets out at 3:15 here, then I head over to the Birmingham campus to teach my 4 to 6 o'clock class there. So I'll be over there in the nursing building on the East Campus from 4 to 6.
Okay.
Okay.
Thank you.
Uh-huh. All right, so you said law of cosines. So how will that work here? We're looking for H, which means we're probably going for what they call I think they call it the main format, right? How will you get H using law of cosines? I'll just tell you, you won't get it directly, but you'll get something close to it. How does that go? H squared equals, was that P squared you said? Or L squared? I couldn't hear. Huh? F squared plus P squared. Second. Minus what? 2 F P cosine H, capital H. Perfect. Okay? Now let's plug in what we know. We know F is 43 feet squared plus P is 60 feet squared minus 2 times 43 feet times 60 feet times the cosine of, we know what the cosine of 45 is, don't we? Square root of 2 over 2. So might as well just put that in. Square root of 2 over 2. And notice this, the 2's can cancel out. Alright, so your H squared will be 43 squared plus 3600. You know what 60 squared is, 3600. Minus 43 times 60. I could almost do that one in my head. That would be 2580. Okay, times the square root of 2 equals. What do you get? Anybody? It's a big number.
1800.
Yeah, okay. But that's H squared. And then what you do? Take the square root of it. So I could see the things going. I can't throw the ball that far. Yeah, I know. Okay. 42.43. Let's see, they say 42.43, exactly. Now, frankly, in my mind, you don't have precision to say that much. At best, 2 digits. So I would say 42 feet, approximately. And that's close enough. A little over 42 feet. Okay? Second?
I have 42.4.
Yeah. Yeah, that's it. 42.4, is that what you said? Yeah, that's 42.43. Yeah. I would have rounded to 42 because you only have 2 significant digits anywhere, but they did 4 significant digits. All right. There is a checkpoint. Well worth your effort there. That gets you out to center field, so you can go with that. There is another, well, let's see how they finish this problem. Okay, the triangle HPF, home the picture to first. H is 45 degrees because that's bisects a right angle exactly, so that would be 45 degrees. F is 43, P is 60. Using the law of cosines from the SAS case, you have H squared is equal to F squared plus P squared minus 2FP cosine H, just like y'all did. And that would be 43 squared plus 60 squared minus 43 times 60 times minus 2 times 43 times 60 times cosine 45. And they got 1800. They rounded to 0.3. And then they took a square root of that. And approximate distance is, if they say approximate, I would say approximately 42 feet. Okay? But they said 42.43 feet, as if you can measure that precisely. Okay. Now, there is one more example there that they are not showing on the slide set, so let's do it here. A ship travels 60 miles due north. So we're going to start the ship down here and travel 60 miles due north. Then adjust its course as shown in the figure here. But they don't tell you what angle it's adjusting it. Just shows you it adjusted it. And then goes, and they call this side, by the way, C, for a reason that'll pop up later. They'll call the initial point here A, and the turning point here B. Okay? And they turn and go up this way, and this they're calling A, and they're calling that 80 miles. Okay? And that gets them to point C, and that's where the C came from. That's a capital C, by the way. Okay? After traveling 80 miles in that new direction, the ship is 139 miles from its point of departure. So that makes A to C here, which we're going to call distance B, 139 miles. Okay? All right. Describe the bearing from point B to C. So here's what we're looking for. That bearing right there from B to C. Okay. We don't have a single angle identified on here. We know what they are, but not the value of them. So what must we use? What? Law of cosine. Perfect. Okay? And we're looking, now what we're looking for with law of cosines, I was going to drag it off again. It must be this class, because twice a day I haven't done it in a long time. Okay. Now, law of cosines will not give us this angle. Okay? No. So the angle we're going to look for with law of cosines will be which one? B. Okay? If you know this angle, because that's in antithesis, this would be north, and that's where you measure that angle from, then this angle will be a supplement to that angle. So you can subtract this angle, from 180 and get that angle. So we're looking for angle B. That's not going to be the answer to the question, but we'll be able to get to the answer from that. Okay? So how does law of cosines work when you're looking for angle B? Cosine of B is equal to A squared plus C squared minus B squared over 2AB. Hey, C. That's yes in Spanish, okay. All right. Got it right? All right, so let's see what we get. 80 squared is 6,400. I can do that one in my head. Plus C squared is 3,600. Minus B squared, I can't do that one in my head, or if I could, but it's going to take too long and give me a headache, okay? And we're going to divide that by 2 times 80 times 60. All right. And I'll guarantee you one thing up front if you need a guarantee. See if you panic if you see it. What you get? That's what that is, right? Okay. Negative 0.9 something? Okay, that makes me feel good and warm and fuzzy inside for two reasons. Number one, from the picture here, it's pretty obvious this is an obtuse angle. I mean, second quadrant, cosine is negative there. Good, wanted that. But also the value, cosine, has to be between plus or minus 1, and this was. Okay, so if you do an inverse cosine of that number you just got, what does that give you?
2.89.
Okay, you must be in radian mode. Okay, so you get B is equal to 166. Point what? 0.15. I'm just going to leave it 166 degrees and subtract that from 180. And that will leave us with 14 degrees. So that would then be, if this is 14 degrees here, I hope I did my math right, that would be point C from B would be north. You always start with whether you're looking north or south. 14 degrees, what direction? That would be west, wouldn't it? Okay. Picture your map there. North is up, east is to the right, west to the left, and south is down. Okay. So north, 14 degrees west. Let's see what they got. They got 13.86, which I count as 14. Because nothing they gave us was more than, well, they gave us two numbers that you could argue could even be one significant digit. We'll count them as two. But I sure don't see how you can get four significant digits out of that. So 14 degrees is good enough for me. All right. Final is kind of an application, but not really. It's kind of an extension or just another feature that looks kind of like it. And this is Heron's area formula. Remember before we did the area of a triangle in the old days, 1/2 the base times the height, right? Okay, that was the area of any triangle. Well, easy enough to get the base. The height was a hard thing to measure. Okay, 1/2 we knew. But that height, exactly what is the height from the point of one side to the perpendicular on the other, hard to tell where that perpendicular is. So that wasn't particularly easy. Then we had, when we did law of sines in the last section, we found another way to do it, which was, 1/2, if you're looking for a sine of one, the area of a triangle, and you know one angle this side and this side is 1/2 sine, 1/2 this times that times the sine of that. Okay. So, but again, usually angles are hard to come by. Okay. Heron's formula is better than either of those in the fact that the law of cosines can be used to establish the following formula for the area of a triangle. The formula is, I hurt my knee over the weekend, so I've been sitting too long. It really hurts to stand up. Once I walk around, it's fine. This formula is called Heron's area formula after the Greek mathematician Heron. This is about 100 years BC, okay, way back there, okay? And here's what he said. Given any triangle with sides of length A, B, and C, you don't have to know an angle, you don't have to know a height, all you have to know is a triangle. You can take a measuring tape and stand at one corner, measure to the next one, measure to that one, and measure between those two. It's pretty easy measurements to make, much easier than heights or angles, okay? But if you know these, then the area of that triangle is the square root of S times S minus A times S minus B times S minus C. What in the world is S? They call it the semi-perimeter. Okay, what it means is add up the three sides, that's the distance around the triangle, the perimeter of the triangle, take half of it, semi-perimeter. Okay? Pretty clever, huh? And it works every time. Doesn't matter whether it's acute angles or obtuse angles. It works. Okay? Now, here's the example 5, which uses this. Find the angle of the triangle having lengths A is equal to 43 meters, B is equal to 53 meters, and C is equal to 72 meters. What would be the first thing you're going to need to determine? Okay, and what is S? $43 meters plus 53 meters plus 72 meters divided by 2, which would be 43 and 53 are 96. That would be 168. Is that right? I'm doing it in my head. Meters divided by 2, which would be 84 meters. Did I do it right? Good. Okay. And what do you do once you know what S is? The area is the square root of S, which is 84 meters, times S minus A, so that would be 84 meters minus 43 meters, times 84 meters minus 53 meters, times 84 meters minus 72 meters. All right. Be the square root of, I'm going to leave off the units for now, 84 times, that I think will be 41, times, that I think will be 31, and that I think will be 12. Anyone got a calculator? Let's do the math. Okay. Now, have you already taken the square root or not? Yeah. Oh, yeah. Okay, you said 0.8. I thought you said times 8. Okay. 1131.89. Is that what you said? Square meters? Yeah. That's what they had in the book anyway. 113. I'm going to round it to 32. Because really you only have 2 significant digits anywhere here. So why you can get 6 out of it, I don't know. Basically, you really should say approximately 1,100 square meters, okay? But I'll let you get by with 1132 square meters. But you can't get 2 more decimal places of precision. It didn't have it coming in, so you can't get it now. Now, I wanted to mention the units. I wrote them in up here. The difference between this is meters. The difference between that is meters. And the difference between that is meters. You have meters, have meters, have meters, have meters. That's meters to the 4th. Taking a square root, that takes half of that, makes it meters squared, which is a great unit for area. Okay? So 1132 square meters. Much easier actually to do the measurements. The calculation's a little messy, but it's not bad. Okay? Whereas the others, you're really guessing at what the height is or what the angle is. There's no way to know that very precisely. So that gives it to you. So they mention again here, there is a checkpoint there for Heron's formula. And there's a little activity off to the side in your marginal note. Well, there's a couple things. Up at the top of part 412, historical note, Heron of Alexandria was a Greek geometer and inventor. His works describe how to find areas of triangles, quadrilaterals, regular polygons with 3 to 12 sides, and circles, as well as surface area and volume of three-dimensional objects. Okay? The reason I say that, in case anyone's looking for a paper topic, there's one, but there's tons of others out there you might want to consider. Then there's these activities determining whether the law of cosines is needed to solve each of the triangles given, and I'll let you play around with that. They give the answers there too. But that's a nice little activity there. And then they have, now I've already said this, study 3 different formulas for the area of a triangle. Standard formula is areas of 1/2 the base times the height. That's what you always did in grammar school, high school, wherever you did it. But the height is a hard thing to measure. Okay. Then we did oblique triangle formula, which is 1/2 BC sine A, or 1/2 AB sine C, or 1/2 AC sine B. And it's easy to measure the two sides. The angle in between those, that's a hard thing to measure. You have to have a sextant or something to do that. Okay, but then Heron's formula, all you need are the 3 links. Easy to get with sound effects, okay? And then use the formula. All right, let's do vocabulary at the top of 413. I know this is one of your favorites. The standard form for the law of cosines, for cosine B, which would be a squared plus b squared minus c squared over 2ac, how would you write that in its standard form? This is the alternative format. What would be the standard form?
B squared equals a squared plus c squared minus 2ac cosine B.
Okay. You said b squared, or what did you say? Hit me with it again.
B squared equals a squared plus
A squared plus c squared minus b squared minus, wait, no, I'm sorry. I think you said it right. B squared is equal to a squared plus c squared minus 2ac cosine. Yeah. Okay, number 2. When solving an oblique triangle given 3 sides, use the blank form of the law of cosines for solving for an angle. Which one do you use? The alternative, I think, is what we call it. Basically, the other form. Okay. Number 3. When solving an oblique triangle given 2 sides and their included angle, use the blank form of law of cosines to solve for the remaining side. Standard form. And number 4, the law of cosines can be used to establish a formula for the area of a triangle called blank blank formula. Say again? Heron's area formula. Perfect. Okay, then do homework exercises. I would do any of the odds 5 through 11. They have pictures. All of those are at Calc Chat. 9's at Calc View. Then do any of the odds 13 to 23. They're at Calc Chat. Then do any of the odds 25 to 29. They're all at Calc Chat. 25's at Calc View. Do any of the odds 31 to 35. They're all at Calc Chat. 33's at Calc View. Then do any of the odds 37 to 43. They're all at Calc Chat. 37's at Calc View. And then there's do any of the odds 45 through 59. Okay, and I would do the ones that are most closely likely to be dealing with your major. Okay. All right. And then exploration. Number 61 is a true false. First figure out whether it's true or false, and then say why it's either true or false. And then there's a think about it for 63, a writing exercise for 65. There's a little proof at the bottom. The 63 is to think about it, and 65 is a writing. Oh yeah, 67 is the first one. Thought I'd already said that. So let's move on. Man, I may have to go clear my head because it's clogging up on me terribly, and it was all right most of the day, but just recently, just the last few minutes, it seems to have clogged. So let's get out of this. Well, let's see. That's not what I wanted to hear. Okay. And move on to 6.3. While that's coming up, what I think I'll do is pause the... Okay. Any questions on chapter or section 6.2? Yeah, 6.2. All right, let's move on to 6.3, additional topics in trigonometry. And this is a pretty relevant one, especially for Daniel going into engineering, right? Okay, and y'all are going into education. Okay. You might run into this as well. Engineers, guaranteed, okay? Y'all might run into it as well. Vectors in the plane. They have to have their seatbelts. No. Okay. The objectives here are to represent vectors as directed line segments, which is basically the primary definition of a vector is a directed line segment. We'll write the component forms of vectors, which is the way to go when you're dealing with vectors. There's other ways you can do it, but it's the best in my mind. We'll perform basic vector operations and represent them graphically. Operations are pretty easy, the graphical. Yeah, it's okay too. We'll write vectors as linear combinations of unit vectors. Okay? And we'll find the direction angles of vectors and use vectors to model and solve some real-life type problems. All right. So the introductory part here, what in the world is a vector anyway? And why do we even mess with it? Well, there's some things like time and mass and energy and stuff like that you represent strictly by a number. You know, 3 minutes, 4 seconds, mass of 85 kilograms, 3 milligrams, whatever. Those are just numbers, okay? But there are other quantities that we represent with a direction as well. For instance, a displacement. Okay. A distance is just a number, okay? 17 miles, okay? But a displacement would be going from here to there. Like if I drove into work this morning, a little more than 17 miles perhaps, but I went from home in Birmingham to Bessemer, which is a little bit to the southwest. Now that's a displacement, because not only is it a distance, but it's a direction as well. And if I were to drive home, and which I will be driving home from here tonight, I will go to the northeast, in the opposite direction. So that's a displacement, okay? You could talk about speed, which is just a number, 65 miles per hour, whatever. But if you talked about velocity, that's not just the speed, but also some direction, okay? So that is a vector quantity. When you talk about acceleration, that's almost always a vector quantity. When you talk about forces, vector quantities. Energy, that's just a scalar quantity. So some things, force, velocity, acceleration, momentum, they involve both magnitude and direction, cannot be completely characterized by a single number, real number. You also need some type of direction with it. So to represent such a quantity, we use a directed line segment, which we call a vector. Now, directed line segment, what do we mean by that? Well, a line, by definition, is infinite. It goes in both directions infinitely, but it's straight, okay? Wherever they're going in space, it's infinite. A line segment, however, is terminal at both ends, okay? So it has an initial point and a terminal point. Now, if all you're interested in is that little line segment, and you don't care which way it started and which way it ended, it's just a line segment some distance apart between 2 points. But if it started here and went to there, then it's a directed line segment. In other words, it has a direction specified. It has a magnitude, just like the distance between 2 points is a magnitude, but it also designates a direction. So one of these points will be your initial point and the other a terminal point. It doesn't have to be going this way. It could be going any old direction, you know. But one place is your initial and one is terminal. Now, embedded in here, they sort of threw this in. When you use this notation for a vector, the first letter listed is always initial point, even if it happened to be over there. That's the P, and the terminal point is the Q, even though that happened to be over there. You're going that way, so it'd be vector PQ. P being initial, Q terminal, from P to Q. And the arrow on top indicates that, you know, whether it's really going that direction or not. That's what it designates. That's one way to designate a vector. We'll see others. The directed line segment PQ has initial point P. When it's written like that, you know that's the initial point, you know that's the terminal point. Okay? Where it begins, where it ends. The magnitude or length is denoted by this notation. Double bars, like absolute value bars, only a double one, with the PQ, the vector written in the middle of it. Okay? Now here's the other way, it's like an absolute value. Always positive. Never negative. Could be zero, but just about always positive. Okay? It can be found using the distance formula. I don't know if you remember that. Do you? Let me write it down. Do you want it in 2 dimensions or 3 dimensions? Let me know. Okay. I'll write it in 2 dimensions because that's where we're going to be living most of the time. The distance formula would be the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? And I'll just use one of these. That's not what we're here for. But if here's your initial point P, terminal point P, this would be x1, y1 would be the coordinates of this point, the initial point. x2, y2, the coordinates of your terminal point. Then the difference in x's would be this horizontal length here, right? Difference in y's would be that. The difference in x squared plus difference in y squared gives you the magnitude of hypotenuse squared, right? That's all right. Pythagorean theorem all over again. So there's your distance formula. 2 directed line segments that have the same magnitude and the same direction, we call them equivalent. Later we'll actually call them equal. But equivalent means equal value, basically, and these will be equal. So all 5 of those, they appear to have the same magnitude, okay, and they sure look like they're going in the same direction. Some are closer together, some are further apart, but they seem to be going. So all 5 of those would be equivalent vectors or directed line segments. For example, directed line segments in these are all equivalent. Okay? Any questions on those? Couple other things in the introduction. The set of all directed line segments that are equivalent to the directed line segment PQ this is a weird sounding set. The set of all directed line segments that are equivalent to the directed line segment PQ is a vector V in the plane. So in other words, vector V is not just that one, but any one that's equivalent to it. Okay? Anywhere in the plane. Now, so here's a second way. One way is to do initial point, terminal point in that order with the arrow over the top. The other way is a boldface, usually lowercase. I have seen them occasionally uppercase, usually lowercase letter. Bolded. Guess what? I don't write bold well, okay? I don't write anything well, but I don't write bold at all, okay? So when I'm doing this and I'm wanting to designate some little vector V, little letter V as a vector, I'll put an arrow over it just like I did over that. That's how in script writing I tell whether it's a vector or not. The text, they can make it bold. Sometimes if it's sitting by itself, it's not really clear whether it's bold or not. That is not bold, this is bold. So near each other it makes sense. This is bold, but it's a different read. The vectors are denoted by lowercase, boldface letters such as U, V, and W. Can have others, those are the most common. V, vector, starts with a V, I think. U, V, and W are quite often used. All right, here's example 1. Show that U and V in figure 613 are equivalent. So what are two things you've got to indicate to let you know they're equivalent? Equal magnitude and equal direction. So which you want to go for first, magnitude or direction? You choose. Magnitude, okay? Magnitude is a good old distance formula, right? Yeah. All right, so let's do that. Which you want to go for first, V or U? I don't care. V, okay? So the magnitude, and again we'll use the double bars. V, I can't write bold, so I'll put an arrow over it. Magnitude of V is equal to, remember how that goes? X2 minus X1 squared plus Y2 minus Y1 squared. Time out just a moment here. Do you notice something? It doesn't matter which one you list 1 and 2 because you're going to take the difference to 0. And whether that difference is positive or negative, it doesn't matter. When you square it, it's going to be positive. Okay? So it really doesn't matter which one you do first. You don't have to do X2, Y2 as the terminal. You can do X1, Y1 as the terminal. It doesn't matter when you're doing this. It will on direction, but on magnitude, it doesn't matter at all. Okay? All you're looking for is a length, which is a scalar quantity. So that won't matter. So what will you have here? This will be the square root of, for V, would be 4 minus 1 squared plus 4 minus 2 squared, and that would be the square root of 3 squared plus 2 squared. That would be the square root of 9 plus 4, which is the square root of 13. One of my favorite numbers in the world. Weird but true, okay? So, we've shown what the magnitude of V was. How do we know what the magnitude of U is? Same thing, only with that. And this actually comes up being much easier for the simple reason that your initial point is the origin. what will this be? The square root of 3 minus 0 squared plus 2 minus 0 squared, which is simply the square root of Can you jump right to the chase? Huh? 13. Okay, you jump right to the chase. You could say 3 squared plus 2 squared, which is the square root of 9 plus 4, which is the square root of 13. Okay, yeah. Anything you want to do there. So magnitudes are the same. Does that guarantee the two vectors are equivalent? No, you must also deal with direction. Now, there's a couple ways to indicate direction. Okay? I think, based on what you've had so far, probably the simplest would be a simple slope. But later, we'll actually indicate this with the tangent of the vector. But guess what? They're going to turn out being very close to the same thing, if not identical. So let's just do them by slope. What's the slope of v? Okay? The slope of vector v. How would you get that? What is slope? Rise over run. Right? And what's your rise here? The change of your y's, that's what goes up, right? The y's are vertical, and the runs are horizontal. So, over x2 minus x1. Okay? Now, I said before, when you were doing magnitudes, or distances, it doesn't matter what you put first and second. Just be sure you get the difference of x and the difference of y. Okay, when you're doing slope, again, it doesn't matter what order you do, as long as you can do 2 minus 1 on both of them, or 1 minus 2 on both of them. But don't do a 2 minus 1 and a 1 minus 2. That really screws it up. Up here, it didn't matter because you're squaring both of them. But here, that does matter. But it really doesn't matter which one you designate 1 and 2, because if you flip that and flip that, you negate this one, you negate that one, and you come up with the same answer you had before. Okay? So again, it doesn't have to be the initial point as the x1, y1, and the terminal point x2, y2, but just keep them in the same order. And what would that be for your vector v? That would be 3 over 2, wouldn't it? Because here was your 4 minus 1. Here was your 4 minus 2. That's 3 over 2. And what is it for you? For you? Okay. Even simpler. Wait, I said it backwards. It's 2/3. Sorry. Y'all got to watch out what I'm saying. I said run over rise. Okay? This is 2 over 3. And what is you? What are you? Okay, never mind. 2 over 3 as well. So, if they have same magnitude and same slopes, or same directions, they are equivalent vectors. So, sure enough, they are. Okay? I don't know, are they going to write on this slide? Yeah. Here's that from the distance formula. It follows that P, Q, and RS have the same magnitude. They did the easy one first. 3 minus 0 squared plus 2 minus 0 squared is square root of 13. And they did RS, which is 4 minus 1 squared plus 4 minus 2 squared, which is square root of 13. So magnitudes are the same. Moreover, both line segments have the same direction because they're directed toward the upper right on lines with slopes of 4 minus 2 over 4 minus 1, which is 2 over 3, which is the same as for 2 minus 0 over 3 minus 0, which is 2 over 3, 2/3. Both of them have the same slopes and same magnitudes. They are equivalent vectors. U and V are equivalent. Make sense? All right, that was example 2, I hope. No, that was example 1. Oh, yeah, sorry. My eyes flicked across the page. Okay. Next thing we do is component form of a vector. This, folks, is the way to go with vectors. Okay? A directed line segment whose initial point is the origin is often the most convenient representation of a set of equivalent directed line segments. Like we saw before, that second one was the origin, much easier to calculate everything. This representative of a vector V is set in standard position. Initial point at the origin, terminal point wherever it's heading. A vector whose initial point is the origin, 0, 0, can be uniquely represented by the coordinates of its terminal point, V1, V2. Interesting here that they chose to name it V1 and V2. V1 would be the horizontal component, V2 the vertical component. Now, here's something to note here, and this is becoming more and more common, this use when you're talking about a point. The coordinates of the point are put in parentheses. Horizontal component, vertical component. If you're in 3 dimensionals, your X, your Y, your Z. That's always in that order. Okay? But that is also the component form of a vector, V, if initial point is 0, 0 and terminal point V1, V2, then the vector V would be, and this, the angle brackets, this is, I'm not saying a new notation, but I don't ever remember seeing this back when I was in grade school, or even I don't think in college. But somewhere along the way this has been taken up as a vector notation, and you put the components of the vector. And since the initial point is 0, 0, its components are V1 minus 0 and V2 minus 0. Whereas that other one we had was 4 minus 3, 4 minus 2. Okay? Its components wouldn't be the 4, 4 because it didn't start at the origin. But if it did start at the origin, then it should be V1 times V2. Always horizontal, vertical, X, Y, X, Y, Z, whatever. That this is a coordinates of a point, this is components of a vector. Okay? Can be related if the initial point is at the origin. But if it's not, they're not related. Okay. Okay. The coordinates V1 and V2, if the origin is a vector, if the initial point is the origin, those coordinates V1 and V2 are also the components of vector V. If both the initial point and the terminal point lie at the origin, then V is a 0 vector, which is a rather strange vector for 2 major reasons. Number 1, it doesn't have a magnitude, or in other words, its magnitude is 0. And even stranger is, it has no direction. Because if its magnitude is 0, which way is that pointing? There's no link there. How can it be pointing anywhere? So it has neither link nor direction. So yet they call it a vector. The one and only one has neither magnitude or direction. So the component form of the vector, component form of the vector with an initial point, not necessarily the origin, P, which is P1, P2, and terminal point Q, which is, whose coordinates are Q1 and Q2, are given by the vector PQ would be angle bracket Q1 terminal minus initial, comma, Q2 minus P2, terminal minus initial. And this difference here is going to be your V1, this difference here is your V2, that's going to give you your vector V, which is one of the equivalent vectors to V, PQ. The magnitude or the length of that then would just be this this magnitude squared plus this magnitude squared, take the square root of it. Square root of v1 squared equals v2 squared. There's how you determine the magnitude of any old vector v. If you know its components, you can calculate the thing. Now, one other good little thing, morsel of information. If the magnitude of any vector v is exactly, precisely 1, then that v is called a unit vector. Uno meaning, you played the game Uno, one card left, so unit vector, magnitude 1. Moreover, if the magnitude of v is 0, that's if and only if v is a 0 vector. Okay, now, most of the time, vectors are denoted by bold, lowercase letters, except for the 0 vector, and it's bold number 0. Okay, only one usually that's designated is a number, and its magnitude is 0. That's a scalar quantity. The vector is a bold case. A vector quantity, but both of the components or all the components are 0, so it has no length, no direction. Okay. How are we doing? I think we just ran over. So, you know, those students that came in here, one of them picked up my pencil and took it with her and did not bring it back. So, I'll remember that when I'm grading her test, okay? With my pen. Okay, where are we here now? We're on this paragraph right under component form of vectors, and that's where we'll begin next time. Okay? Good deal. Any questions so far on vectors? I think you might be able to do a little bit with the homework exercise. Boy, this is a fairly long section, so we'll go most of the next time in this section. Maybe not get out of it. We'll see. I think you can do number 9 for sure. And then and that's at calcchat.com. Try to do either 11 or 13. They're both at CalcChat. 11's at CalcView. I think you can do 15 or 17 as well. I think you can do any of the odds 19 to 23. They're all at CalcChat. 19's at CalcView. And let's hold off that and we'll do the rest of those next time. Any questions? All right. Sad thing coming up. Last day of class. Get over it. Okay. Yes.
When's the last day we can try and get that help or something?
You'll have to ask financial services that. I imagine you can still apply. The question is whether the results will be back in time for summer. The sooner you submit that application, the more likely it is it will be ready by the beginning of summer. But I can't guarantee what that is. I doubt if they can. But they can, I bet you that's what they're going to say. Apply as soon as you can. It may be they don't guarantee it's back by then, but it might come back by then. So, sooner you do it, the better.
Thank you.
Uh-huh.
Have a good one.
You too, thanks.